Hello everyone, it's July the 2nd. Let's go to it. What do we have today? Find k closest elements. Given a sorted array, two integers k and x, return the k closest integers to x in the array. The result should also be sorted in ascending order. An integer a is closer to x than integer b if the absolute value or absolute value is the same, but a is smaller than b. So we give this two integers, return the k closest integers, the four closest integers to 3. K closest. So the one closest, so wait, hold on. K closest to 3. So 2, right? 4. And the result should also be sorted. So we can sort at the end. But 2, 3, right? 2, 4, right? That's the immediately. And then 1, 5. But 1 is closer than 5 because 1 is smaller. K closest, why do we include 3 as well? Because 3 minus 3 is 0, so we always include the number itself. So we include the number and we go from the center to the outside, right? So we compare on both sides. So we have the center. Oh, hold on, this x is not, doesn't have to be inside the array, just any x. So here, if it's -1, so -1, so we binary search to locate where it is, and then it's going to be this. Okay, so 3, binary search, it's inside here. So it's this one, this one, this one. I see what we're doing. So basically, we need a binary search to locate where the number is going to be. And after that, we go, well, I mean, we have to first check if the number is inside the array. If the number is inside the array, that one will be included. Okay, k array.length. Can we do it? Yes, we can. We can. We don't have to sort. So k, we have a k, and then we have something in the front, something at the back, right? And then we just say we compare the front and the back after we compare the itself, and we'll compare front and back, see which one. See, first we check the absolute value, and the one is smaller, we add it, and then we move to the next one. Check again, the smaller, if the equal, we check. Yep, I think we have a solution. And we don't have to sort again. And of course, we can, but we can save on the sorting. Yeah, we can save on the sorting, but we do have to extend, or like have to add them together, because we're going to have two arrays, right? One array recording the value in the front, and the other array recording the value at the back. Oh, we don't have to actually. Oh, do we have to? We don't know, right? We know the final length, but we do not know where the things are going to be. When we do the back, we just append. When we do the front, I mean, we can append the front if we're using a deck. But that seems to be a little bit more complicated. We can also just append, right? After append, we just need to reverse it. Okay, that's fine. So we're gonna have front, left, and right. Left, right, they both equal to this. We have to use binary search. So from bisect, import. Let's do bisect right. All right. And then we are going to first find the index. So the mid, right? Mid equal to mid. What if it's not? It's not, then we're gonna go left and right. So mid equal to bisect right array and x, right? And we say if array mid, well, if it's equal, we're gonna go to the right. So with -1, if array mid -1 is equal to x, then let's call it small and big, small and large, small and large. And I want left and right to be here. So we have left, right, and equal to mid, right, and equal to let's do this. If it's equal, so we have found it's equal, then large dot append x, right, and left right equals mid -1 and mid +1, right? Else we go left right equals now we insert in the center, so it's going to be mid -1 and mid, right? Now we have to also consider -1 is going to be inserted as 0, right? 0. So we check that's not true, so it's going to be here, and it's going to be -1 and 0, right? -1 and a 0. These are different situations, or how can we? No, dummy might make things more complicated. So just consider it's here, right? So it doesn't have left, it doesn't have right. So right equals 0. That's actually fine. What if it's here? Then it's going to be here. Mid is going to be here. Mid -1 is this one, and mid is the right. So we just have to set a condition. So now we're ready. We're just going to go to both sides. We say while left is larger equal to 0. Or no, that's not what we want. What we want is while len small plus len large is smaller than k, right? And then we say if left is larger equal to 0, then we have a candidate, right? So we get a candidate. So if left is larger than we candidate, so we can do this, right? So can L equals array left, if left larger than equals 0, else math.inf, right? Just we do a math.inf. I'll make it. It can be right. It can be right. If right is smaller than n, I'm gonna set here n equals len array, right? If right is good, else if right is not good, we'll just set an inf, right? Then we're gonna compare, right? We're gonna say if ABS, well, we don't have to do ABS because we know x minus cand left is smaller than can write minus x, right? Then a is closer, then we say, what do we say? We say small dot append can left and left minus equal to 1. Elif x minus can left is larger than can right minus x. Then we say large dot append can right and right plus equal 1. Else, if they're the same, then the Elif is the same. Elif can left is smaller. Oh, can left will always be smaller, right? Because we're going out, so can left will always be smaller. So we can just say else. Else the small dot append can left and left minus equal 1. Yeah, these two conditions can be combined. So we can say if this or, oh, so smaller equal to, right? If it's smaller equal to. And then this one can say else, right? And until it's done, right? Then we're going to return small, have to reverse it, plus large. All right, let's take a look. We have two test cases. First one, 1, 2, 3, 4, 5, and k is 4, 3, result 1, 2, 3, 4. Second, same thing, 1, 2, 3, 4, 5, and 4 minus 1. Answer is 1, 2, 3, 4. It's like the same. Okay, so what we have here is array k x. This is going to be fine. Closest array k x. All right, check. Oh, the first one we do not pass. 1, 2, 3, 3. I think the left and right is mistaken. So this one is equal. So large append x. Yeah, and then mid. Oh, hold on. Left and right. So left. Maybe we could combine these two situations together. So we find it, right? No matter what, we find it, and we can always say the left. So I think we don't even have to check this. I think we can just say mid and then do this. Mid equals this, left and right. Okay. Let's try it. Some other test cases. I don't know. Let's say, let's just go for it. All right, test case. Array size 1. 1, 3. It should be 1. All right, let's try it. Pending. Accepted. Nice. This is not too hard. So binary search to locate x in array. Then we go both sides. We go left of left to x, left of x, and right of x 1 by 1. Comparing the difference to x with x. We include the choice. We include the smaller choice, and keep moving. Let's be more explicit. We go left, comparing this. If the left candidate is closer to X, we include it and move more to the left. The same goes with the right candidate. The process ends when we have enough candidates. We have accumulated enough closest elements. O(n) log n for sorting, not for sorting, for actually it's O(n). O(n) because this is log n and this is most run O(n), and this is also O(n). So yeah, it's O(n). Let's see, middle of the pack, 296 milliseconds, 67% ranking. All right, and look at the solution for this. It might be labeled as medium, but now this is like one of those soft medium questions. I don't think I've done this before. 658. Okay, so this is LeetCode 658. All right, sort with custom comparator. Binary search plus sliding, that's called sliding window, yeah. Log n plus k. Oh. Log n plus k. Ah, this is a better way to say, yeah. I shouldn't say log n. Log n plus k, where n is the length of array, and k we know what k is. Yes. Depends, yeah, depends. Binary search to find the left bound. Oh, it's even faster. N minus k plus k. All right, so the first one, check every number in array for its distance and sort the numbers by this criteria. Then the answer will be the first k elements. Really? Let me think. What if, yes. I guess this will pass as well. I never thought about this, and the solution immediately coming to my mind is the binary search, not this. But I think this one is fine too. But you have to sort array with the key. Nice. Result. Take the first k and sort it. Yep. And k log k. Yep. And then this is my solution. Binary search. All right. Binary search. Oh, right minus left minus 1. We can do that. Yeah, that's true. And then you can do that. Return the window. Then we don't have to handle all these things. Yes. Oh, wow. That is smart. If left equals this, right plus 1. Left minus 1. I want to redo this. This is good. And I have a little base case. You see that? I have a little base case. Nice. Very good. Very good base case. We can make it simpler. Okay, so yeah. Sliding window, that's the word. Sliding window. Alright, let's try it. Let's implement ourselves. So this is the same solution, right? The same solution as my solution, but so it's gonna be, this is the this is the same, come on, this is the same solution as mine, but with better implementation. Reference. Yeah, I think it seems like I say this every single time. It's always has better implementation than mine. Notice that we don't have to use extra space to save the candidates because the resulting array must be bounded by left and right pointers. Yeah, so we're gonna copy some, so not this, right? And then just copy the rest. We're gonna make significant changes to it. So this I like, we get a left and right. And then this is gonna be right minus left plus 1. That's going to be the length. Hold on, what is the length? Well, the length is right minus left. Oh, the little details. Let's observe the length. The length. So in here, we say we start, left is here, right? Right is here. So the starting point, we shall have no length, right? If we start here, then we say the starting length is 2. But no, the starting length should be 0. So this should be minus 1, right? There's a starting length, you don't have anything. And then we have candidate left, candidate right. I actually like my way of doing the 2 candidates. And say if this is smaller than this, then we don't have to append anything. We acknowledge it, so we just do left. And if this, we acknowledge it, then we do right. And once we included everyone, we say when the return, we don't even have to sort. I think we just return array left. This left is going to be, oh, what do we return? Left is not including, right is not including as well. So it's going to be left plus 1. Yeah, so both are not including to right. Right? So solution 2, pass. Good. This is a good one. I like this one. Simpler. And we don't even, we have to have and is here. Yep. There's much better implementation. I think this one should be faster because we don't have to handle extra arrays. It's fine. And just slap in the face. That's alright. Alright, I have one more solution to go through. Find the left bound. That is true. If we find the left bound, then the resulting value must be, yeah, how do we find the left bound? And independent of k, first of all, what is the biggest index the left bound could be? If there needs to be k elements, then the left bound's upper limit, that is true. Because if there were any further to the right, you will run out of elements. Binary search is typically used to find if an element exists or where an element belongs, yeah? The beauty of algorithm lies in how abstract they are, with some clever thing we can apply binary search in a unique way to move our left and right pointers closer and closer to the left bound of our answer. Let's consider 2 indices at each binary search operation. There's your mid and the sum index. The relationship between these indices is significant because one of them could possibly be in the final answer. For example, if mid is this, k is this, then array 2 and 5 cannot possibly both be in the answer. That will require taking 4 elements. So to the question, how do we move our pointers? If the element at array mid, if the element at array mid is closer to x than that, then it means this. Otherwise, every element to the right of it can never be in the answer. It means we should move our right pointer to avoid considering them. And move the left pointer. I might understand, but I still need to think about it. So what it says is, we find where it is, right? And then we look to left and right. So we know the left has to be this. So we're basically trying using binary search to find the left bound. Hold on, let me read again. Actually, I don't want, let's see this one. This was good. So k is 3, x is 4. So we know, so k is 3. So we know the upper bound of the left, yes, of the left boundary. The upper bound of the left bound is here. And the lower bound of the left bound is here. Then we just move these, trying to find where the upper bound, where the left bound is. So we compare both to 4. So this is 3, this is 2, right? So this is closer, right? So this is closer. If this is closer, that means the left bound must not start from here, because we'll have a better option somewhere here. Hold on, it's playing. No, don't play. I am not done thinking. We need to find the leftmost index that will be in the final answer. Farthest right, it could be yes. Otherwise, yes. So we say the mid is here, right? This is the mid. And we're going to compare the mid. So mid compared to 4. And right compared to 4, because we want to shrink, right? Want to shrink. So what we want to know is if this, if the mid can be the index, the left bound. So we find the mid, and we say if mid is the index, then we find mid plus k. Right? So this is the left bound, this is the right bound. Then we compare the left bound and the right bound based on the mid. And we will arrive at a conclusion that one side will be bigger than the other side. Right? Then the side that is smaller, that we need to keep. Because the whole point is to find the leftmost bound, right? So we're trying to find the leftmost bound. So among these, hold on, let me try it again. At each binary search term, usually mid and the sum index, right? So this is the mid, and this is our supposed bound on the left and right. The relationship between these, only one of them could possibly be in the final answer. So either this or this. If mid is 2, k is 3, then array 2 and array 5 cannot both be in the answer, since that will require taking 4 elements. That is true. That is true. So one of them, so yes, the left and right must be one of them. So we just choose. We choose the smaller one, right? We choose the smaller one. If mid is closer, then mid plus k cannot be. So the leftmost bound must be smaller than that. Cannot be in the answer. I think I see think I see. So we take with binary search to take because the answer must be a subarray of the original array, right? The answer must be a subarray. So the question is just where the subarray lies, and we try to look for the left bound. So with the left bound, we know the right bound. Actually, one larger than the right bound, and we're trying to see which one is closer. And then we know one of them must be in the answer, right? One of them must be in the answer. It's possible that they both not be in the answer, but because we already set the boundary, our initial boundary, so we know that it has to be somewhere in there. Right? It has to be somewhere in there. I mean, it could be, right? If the k is really small, now it could be both do not belong. Right? Both do not belong, but we know one will be larger than the other. If one is closer to x than the other one, right? Then we know we can take the smaller one, right, and the larger one will not be, that one will not be in the answer. So the two might not be the, so in this case, right, so array 2 might not be the real answer, but between array 2 and array 5, we know if array 2 is smaller, is closer, then array 5 must not be, and no matter what, it cannot be. It could be something array 2 or maybe even smaller than array 2, but it cannot be array 5 because we can find 2, 3, 4, right, which is a better answer compared to the other one, because the other one will have to involve 5, but 5 is not as close as 2, so anything 5 or beyond we can eliminate. Therefore, we can move the right pointer to my pointer, yeah, we can move right to where? To here, to mid plus, I can say to mid plus k. We can move right to mid plus k. Right, so let's see. So this one and mid plus k, and then we compare this one smaller. So this will go with now. So we're going to move right actually to 5. Right? Oh, hold on. You're not moving right to 5. You're moving right to the mid. I don't understand. 3 is closer to x than 6. 6, 7, 8 can never be, since that would imply 3 is not in the fundamental, but we know 3 is closer to x than anyhow. Yeah. So we know 3 must be, so the answer must be, like, it must not be this, right? So why do we move the right to here? Because the left and right, we're trying to find the left bound, and 3 is the current. So yeah, this is our original. Our original, we say the left bound is between this, and we find the mid, right? And we say between this and this, we need to choose which one is more likely to be the left bound. What if this one is closer? Then we move the left pointer. If this one is closer, yeah, like the thing is here, then yeah, then this is more likely, right, to be the target. So we move left all the way here, right? Move left all the way here. Now we move left to here, the possibility. Right? So move left to the mid. So we say mid of this, one of these can be the left bound, and we choose one, right, to be the left bound. If this one's closer, then this is likely to be the left bound, so we move the right to here. If this is likely to be the left bound, so we need to move the left here. So we say anything larger than this is not possible. Here we say anything larger than this is not possible. Then we move the left to the mid. It feels weird, right? We move right to the mid or move left to the mid. We'll move right to the mid because we think 3 is likely to be the left bound. It has to be 3 or something smaller than 3. That's correct. If 6 is closer, then it has to be 6 or something larger than 6. No, 6 or something smaller than 6, because it's a left bound. So 6 or something smaller than 6 but larger than 3. That's why we move left to 3. That's correct. So we move here, then mid is here, then we compare again. That's 2, that's 1. Ah, this one is closer now. 5 is closer. We have 4. 2 or going down is not going to happen. So left will move to 2. Oh, left don't move to 2. Left move to 3. Because we know 2 is not likely, so we can do +1. So move the left pointer, we can directly move to. So now we found it. As left is no longer less than right. This concludes, and we have found the leftmost index. Nice. Oof. At each operation, we compute the mid and compare the two elements. The element at this is closer, then move right pointer to mid, right, to mid. If element this is closer, we move the left point to mid +1. The smaller element always wins when there is a tie. Yep. Alright, let's try code this one up. Oh, this, I don't think I can come up with this even after reading this, right? It's like, if I do this problem again, say a month later, I think I might be able to come up with this version, but like not this version, but this version, but this is something else. This is something else. Smarter binary search. Search only for the left bound. Reference is the same, but we're still going to copy and paste. Okay, copy and paste here. Okay, so here's what we're going to do. We're going to have a left and a right. Left is going to be 0, right is going to be len array minus k. Right? Is that correct? 5. Yeah. 2, 3, 4 minus 3. Yeah, that's true. So we have a left and right, and then we're going to say while left is smaller than right. Mid equals left plus right divided by 2. And then we're going to compare, right? So we say mid is a likely candidate, right? But then we have to say either mid or mid plus k. So these two, we're going to compare, see which one is closer. So both are likely to be the left bound. So we say if array mid minus x, we don't know which one is larger, so I think we have to do ABS. ABS, this is smaller than ABS array mid plus 5 minus x. Actually, it's smaller equal to, because if they're equal, we always take mid. So when this is the case, then we take mid. So mid is more likely. So not like mid is more likely, is the left bound must be at most mid, right? At most mid. It could be, yeah, at most mid. So I'm going to say left bound is at most mid. So we do right equals mid. Else, I'm going to say left bound is at least, right, is at least mid plus 1, because we cannot take mid or anything smaller than mid. So we say left equals mid plus 1. And we'll run this until we get out. And once we get out, we can just return array left and left plus k. So solution 3. Oh, we have an index out of range. Why did you add 5? Should be add k. Nice. Very, very good. And bravo on this solution. Submit. Maybe this is the fastest. Oh, we have a wrong answer. Ay, ay, ay. Oh, it's something we did not consider. Hold up. Hold up. Interesting. So, solution shall be expected 233. 233, but we get a different one. All right, let's take a look. So we start with 0 and minus k. So 3, 1, 2, 3. So here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 minus 3 is 6. 0, 1, 2, 3, 4, 5, 6. That's true. So we have these two. And left is smaller than right. And mid, that's 6. 0, 1, 2, 3, 4, 5, 6, 3. 0, 1, 2, 3. So mid is here. Right? And then we're going to compare. We say mid minus x, x is 3, that's 1, and these two are the same. Then we're taking this, but we shall take this. What happens when the two are the same? That is interesting. Hold up. If 1 is smaller, then we definitely go there, but if the 2 is the same. Now, the 2 is the same, there are two situations, right? So it could be 2 and 4. In that case, we gravitate towards 2. But in this case, it's 2 and 2. If it's 2 and 2, like they're the same, they're both on the left side. And we're trying to say this and this. How do we gravitate towards the right side? So we say if ABS is the same, right? We're sure that ABS is the same. Then we'll have to compare on the value as well. We have to compare on the value. If the two values are the same, then it also depends, right? Cool. I don't know, because the solution seems to be very short. It's very short. Oh, it didn't use ABS. X minus mid and this minus x. Is this just because of luck? I'm doing ABS because I don't know where x stands. X could be in 3 different locations. Analyze it, right? 3 different locations. If x is in between mid and mid plus k, then it's going to be x minus mid and mid plus k minus x. That's true. If mid and mid plus k are both to the left of x, then we do x minus x minus mid and mid plus k minus x. That also makes it so we want to gravitate towards mid plus k. So mid plus k minus x will be a negative value, which will be good, right? Which will be good. If mid and mid plus x are both on the right side, then we're going to gravitate towards the left. So we say x minus mid is going to be negative. Nice. Oh, this is also a trick here. This is a trick. Yeah, this is a extra trick. So let's say there is an extra trick in the if statement. When given mid and mid plus k, let's be more explicit. So I'm given mid, given array mid, right? And array mid plus k, there are 3 positions where x can be. If x is in between array mid and array mid plus k, then we compare x minus array mid and array mid plus k minus x, and we compare this, no issue. If x is larger than array mid plus k, then we must gravitate towards array mid plus k. Luckily, interestingly, doing comparing x minus array mid and array mid plus k minus x does indeed help us gravitate towards array mid plus k. Similarly, if x is smaller than array mid, the same comparison will also allow us to gravitate towards array mid. So that is the trick, the last trick of the solution. Nice. I mean, yeah, we do have to think about it. Oh, this is fastest. Look at this, 276 and 90% ranking. Nice. All right, that's it. 3 solutions. Good question. And then the last solution it's pretty difficult. I think it's pretty difficult. Pattern search, 2-pointer. What type of 2-pointers are you talking about? Yeah, I think it's the regular one. All right, that's it. Oh, and the runtime. Yeah, let's take a look at the runtime. So the runtime, because we are binary searching n minus k, yes. Binary search n minus k, and then returns. Okay, that's good. All right, that's it. That's it for today. I'll see you guys tomorrow for the difficult one. Adios.